In January of 2014, Nature published an article that was promising to revolutionize cell biology. The paper, titled Stimulus-Triggered Fate Conversion of Somatic Cells into Pluripotency, described a simple protocol that could convert adult differentiated cells back into stem cells. Or, so the authors claimed. Though the feat itself had been achieved before and was even awarded with a Nobel Prize, this was an unimaginable breakthrough. The stress method did not require swapping of the cell nucleus or the use of transcription factors. All that was needed is an acid treatment. If as effective as described, the result could be achieved in almost every cell culture lab using basic lab equipment. So, laboratories around the world rushed to replicate the results. They tried and tried again with absolutely zero success. At the same time, people began to notice inconsistencies in the original and follow-up papers. Major issues such as methodological flaws, plagiarism, and fabricated images were uncovered. An independent investigation was launched to check for evidence of scientific misconduct. It brought to light glaring errors, including signs of purposely contaminating cell cultures with embryonic stem cells. The papers were retracted less than a year after the original publications. The lead postdoc, credited with the invention of the method, Haruka Obokata, was stripped of her PhD, while another collaborator, a prominent developmental biologist, Yoshiki Sasai, took his own life. Dex regarded the paper cutouts scattered on his desk. As usual, he had received a new case in a vanilla envelope, placed on his windowsill at the crack of dawn. The story was perplexing. On one hand, the crime had been solved and the criminals punished. On the other, the two retracted papers seemed the very tip of the iceberg, with truly powerful culprits hiding in the deep. 4% of scientists anonymously admitted to fabricating their data. The infection had spread through the system, and Dex, of all people, was tasked with tracing its origin. He leaned back in his armchair and kept leaning until he realized the chair was likely broken, and he would fall backwards if he wouldn't stop. He counted the coins at the bottom of the envelope. It wasn't even enough for a pack of cigarettes. Luckily, Dex didn't smoke, which left a sizable amount of funds to purchase pins and colorful stickers with cats. He arranged the pieces of the board and grabbed his trusty notebook. Whatever was at the bottom of this data fabrication crisis, he would dig it out, even if it meant getting dirt under his fingernails.
Hi, my name is Masi. I'm a PhD student of evolutionary biology who enjoys screaming into the void in front of a camera. This is Dumpstify Data, a series in which I analyze the hell out of crumbling institutions. Over the next few videos, I'll be talking about academia with a focus on STEM and sciences, and oh boy, there is a lot to talk about, because, and I'm being deadly serious right now, science is in deep trouble, and I need people to know why. In this series, I'll be going over the many issues that science as an institution is dealing with this century. You don't need to watch them in order or catch up on every single episode, they're all standalones. However, they will occasionally reference each other, and I will keep updating links as new videos will appear. Today, I want to tell you about what happens when we don't make our science open and collaborative. Enjoy. Here is a rather obvious fact. Scientists are human. We can make mistakes, intentionally or not, we can have gaps in our knowledge of statistics, we can become overly attached to our data and discoveries and hoard them like magpies. It's the nature of human fallibility, ultimately unavoidable but in need of addressing. And instead of addressing it, we're kind of pretending that scientists should just convert themselves to Cybermen already.
Upgrading is compulsory.
I started this video with the stem cell scandal because it covers almost every point I'm about to make. I highly recommend this article, which goes into detail about the story. With STAP, everything that could go wrong did, which is probably why the mistakes were exposed so fast. Not every instance of scientific misconduct is as blatant, and by far not every instance is eventually caught. In the hierarchy of science fuck-ups, we start at the top with fabricating data. I'm talking straight up inventing a number out of whole cloth, photoshopping an old western blot to look new, describing an experiment that was never conducted, and so on. Fabrications are rare, both because it is easier to spot and because it's not something that you can do without intent. On the whole, scientists aren't bad people. Most of us wouldn't go so far, even to keep our jobs. However, when I say rare, I'm not talking about individual instances, I'm talking percentages. A 2009 systematic review and meta-analysis, for example, found that 2% of scientists anonymously admitted to fabricating data, and 14% say they knew a colleague who did. 14% is not a small number. If a survey of restaurant chefs would show that 14% of them do not wash their hands after going to the bathroom on the job, there would probably be a media outrage. Another study from 2021 in Denmark got over 4% of anonymous confessions among their 6.8 thousand survey respondents. And statistical methods indicate that these percentages are actually underestimates. So this is not great, and before you say, but Matthew, surely these people get caught and their papers retracted, we'll come back to that. The second type of scientific misconduct is umbrella term questionable research practices. They happen in many ways and at every stage from planning an experiment to publication. There's formulating a hypothesis after looking at the data to pick something you are likely to confirm, harking. There's leaving out data that doesn't fit or getting rid of too many outliers. And there's a myriad of tiny ways, from instances of microplagiarism to fixing that graph just a little bit, to half-assing the lab protocol because it was 7 PM and you really wanted to just go home already. To some extent, I get it, science is really hard. Being at your 100% capacity 24/7 is impossible, especially when you're working overtime, which many of us are forced to do. There's also a powerful, often subconscious drive to get significant results. A very common kind of misconduct is p-hacking, or the practice of adjusting your data until you get a significant p-value. For the non-scientist in the audience, I will have better explanations in further reading, but the extreme brief explanation of p-values is that it's the probability that you got this result by pure chance. For some reason, the cultural scientific convention in natural sciences is that a 5% probability of accidental results, so a p-value of 0.05, is enough to claim statistical significance. There are a lot of problems with using this metric, and I will talk about it in future videos, but for now, just remember that we want the probability of our results being accidental and meaningless to be under 0.05. So, how does p-hacking happen? Well, let's say you are running an experiment and you originally planned to have a sample size of 200 subjects per group. After finishing and running your fancy statistical analysis, you get a probability of a significant difference between your groups of 0.07. That means that there's a 7% chance that your experimental treatment didn't actually do anything, and the difference is a fluke that won't repeat if you run the experiment again. Well, you can admit a negative result and call it a day, or you can decide to sample another one, and another one, and another, till you get to that sweet 0.05. This really reminds me of my undergrad days when me and my friend were measuring pH for an exercise in chemistry lab. And measuring pH is tedious and sometimes takes a really long time, and we knew what the result is supposed to be. So we would measure it precisely until we would get the number we wanted and write it down. P-hacking is similar. In your head, you already have an idea of what the result should be, so you push the data to fit that expectation. And you know the worst thing? A lot of scientists don't even know that this is bad. A recent study found that it is abundant across life sciences where P below 0.05 is the golden standard. And in my personal experience, a lot of researchers have never even heard of the term. Also unrelated, but while I was researching this video, I discovered that there is a mathematician whose name is literally Paul Hacking, like his name on papers is P Hacking. This might be the best example of nominative determinism that I've ever seen. In the studies that I mentioned earlier, between a third and a half of respondents admitted to questionable research practices. If you are a scientist and are watching this, chances are you've done it as well, or you know someone who did. And sometimes you just didn't know any better. Many of these instances are honest mistakes. But they are abundant, and we have no idea what kind of impact it makes on the field. We barely even know the extent of the problem. Now, that was very scary, to me at least, and I would really like to follow this up with some good news. I want to say, yeah, it looks bad, and it is, but we have a mechanism to deal with it. Peer review, retraction, and replication. When people mess up, it gets caught eventually. Right? Well, it depends. Let's start with peer review, a process in which a paper submitted to a journal is sent out to experts in the field to be checked. It is another gold standard of good scientific journals and a necessary first line of safeguarding. However, it's not nearly as effective as we would like to believe. It works, sure, but as a rough filter. Think about it like wearing a seatbelt. It prevents a lot of harm, but it is not a spare the dying cantrip. Remember, peer review is done through unpaid labor in an honors system. Peer reviewers are other busy scientists, not journal employees. They are also often selected by the authors, which adds another layer of messiness. Again, scientists are human. Sometimes we are tired and just want to get it done as fast as possible. Sometimes we are personally invested in a hypothesis or a research group and want them to get published. And sometimes we simply don't catch the mistakes, and that's okay. Peer review is the bare minimum, it's not supposed to be the whole deal. Thankfully, we have further safeguards in place. In theory.
Good guess, but actually no.
Let's say an article with fabricated data gets through both peer review and the editorial team. Common wisdom goes, sooner or later someone will notice and the article will get retracted. Well, sometimes they do. Retractions are pretty damn rare, they happen around 0.1% of cases, and on one hand this might mean that bad research doesn't get through in the first place. On the other, there are people like Elizabeth Bick, whose entire job is to be science detectives, going through published articles looking for signs of fraud. And, according to Dr. Bick, when the instances are found, journals rarely jump on to remove the article as soon as possible. A 2013 study found that it takes an article around 13 months on average to be retracted. That's almost 3 years. Plenty of time for people to build their citation lists and future plans based on flawed data. And that's if the article gets retracted at all. In fact, according to Dr. Bick, many journals simply ignore emails about serious issues in the articles they published. Retractions aren't their priority after all. No one gets paid for removing an already published piece, and admitting to a retraction is a reputational risk. So, even though the number of retractions has increased significantly in the last couple decades, it is still not enough. An average social media user deletes more old problematic posts than a journal retracts its articles. Okay, fine, this is all deeply concerning, but at least we still have our last line of defense: replication. Ideally, every hypothesis testing research is supposed to be replicated multiple times to eventually become a part of a meta-analysis. In reality, we are in a replication crisis. I will dedicate a whole video to it, but to put it bluntly, replications are not very common. For many reasons: financial, structural, ideological. Replicating other people's studies isn't as exciting as doing your own thing. It's much less likely to get you funding or land you a publication in a prestigious journal. And sometimes it's really difficult to do, because scientists kind of suck at describing their own methods. See, in order to replicate something, you need to know exactly how they did it. That's what the method section is for, a boring, meticulous instruction describing every tiny step that led to the results. Supposedly. In reality, method sections of many papers are confusing and vague, and trying to replicate such paper is like trying to recreate a TikTok recipe.
Everybody's so creative. So what you got there? Some leftover macaroni and cheese? I got leftover macaroni and cheese, but it don't look quite like that.
Vague methods happen for a lot of reasons, ranging from silly to petty. Sometimes you just can't be bothered to describe everything in enough detail. Sometimes you forget what you were doing and have no way of tracing it back. That's all in the realm of honest mistakes that are hard to eliminate completely. However, details can also be left out on purpose, because you don't want to share your super secret lab technique that you invented at grad school, because your supervisor told you not to publish the R code, because the original data is the intellectual property of your institute and you are not allowed to make it publicly available. This is a completely separate issue from open access articles, something that I will also come back to in a video about academic publishing. This is a result of culture of secrecy, of intellectual property over discoveries, of petty competition and fixation with being the best and the first at something. And also forgetting to write down what the hell you were doing. I want to say no shade to the second one, cause I learned this the hard way in my masters, but yeah, we need to do better. In conclusion, there are issues, but there are also ways to solve them. It is hard for me to strike the balance between critique and hope. On one hand, I don't want to sugarcoat the issue and make it seem like everything is fine. On the other, the scientific method is still the best and the only effective strategy we have for discovering new things about the universe. The system is flawed, sure, but it's the best we've got, and there are many ways that we can try to make it better. First of all, peer review should be a job. Maybe not a full-time job, but also not some extra chore that you have to pile on top of your already overbooked schedule. It's also not supposed to stop at journal acceptance. A culture of continuous, constructive criticism and support has took the stab paper out in months. This is what should happen with every deeply flawed paper, not just the ones that generate a ton of media buzz. When the issues are exposed, they should be addressed, and not after 3 years of being left untouched. Journals do not have an incentive to deal with retractions, and this is something that has to change eventually. In the meantime, there are intermediate solutions. Get to know Retraction Watch, a volunteer-run project that tracks flawed research and informs the scientific community. Use their database and support their efforts. Often enough, they're the only ones setting off the fraud alarms. Increasing the transparency of scientific research should also be a key priority. Apart from raising the standards for describing methodology, we can also encourage data sharing, with badges for example, and focus on keeping our data, code and knowledge open access. Science should be available for all. We can't keep patenting fundamental research and life-saving technology funded on taxpayer money. We can also address some deeper issues that lead to fraud and misconduct. Like, not to be an idealistic romantic, but I thought this whole scientific endeavor was about understanding the universe and making the world a better place. And what are we doing instead? hiding our discoveries from each other and fighting to be the first in line to the next big paper? Aren't we in this together? Like, shouldn't we be sharing everything and uplifting each other instead of being pitted against one another in a competition? There's a prevailing, persistent misconception in society that science is done by great people, brilliant minds that win Nobel Prizes and get their names cemented in textbooks. Well, this is bullshit. Science is done by enormous teams of people, each contributing one little piece to the net of knowledge. The Nobel Prizes often go to the powerful, the lucky, the ones managing these teams or being precisely on time to make that one last step. And this isn't good for us. Science shouldn't be a race because a Hunger Games system does not prioritize solid, honest, meticulous results. It encourages fraud, misconduct, and secrecy and takes us away from our real goal. Like, what do you think happens when you reward scientists with jobs and promotions for getting the most papers published instead of doing good science? So, if you're in STEM, your employment and salary depend on your impact factor, on how many papers you can put out in a year. I know that, and I also hate it, but remember, this isn't what you're here for. You are here because you got curious, and the curiosity never stopped motivating you. Focus on the curiosity, at least in your heart or at the back of your mind. We aren't competitors or enemies. We are in this together. So stop trying to get ahead at the cost of sacrificing the science.
Dex Darkly felt more lost than he did 5 days ago at the beginning of his investigation. Some pieces were clicking into place in his head. Others were jammed forcefully into corners or fell under the sofa, never to be recovered again. He scratched the tip of his nose and spun around in the chair. Dex was starting to suspect that the conspiracy spread considerably wider than he originally anticipated. One thing was certain, though. He was going to expose every node in the spider web, step by step.
Hi, hello, thank you so much for sticking around. I am really excited. This series is my baby and it has been in the plans for such a long time, and I'm really happy I can finally share it with people. So, about dumpster fire data, the target audience for this series is mostly other current or future academics. However, I am trying my best to make it accessible to everyone, and that's why I'll be putting together a lot of helpful materials in a citation and further reading documents, link in the description as usual. And all of this stuff is serious, and we should be talking about it. So please do. Start a conversation over coffee with a colleague, ask your professor about some of these topics. If you know of issues in your own institute, complain about it, anonymous or not. Share the video, it helps both the cause and the channel. If you want to catch all of the future episodes, make sure to subscribe and turn on notifications. I'll try to keep the posting schedule more or less consistent, though it depends on how much time I will have. I'm a full-time researcher. But if you want to support the channel, like and comment on the video. Give me your gossip, tell me about your ex-supervisor that does all the bad things. I love this shit, I want to know. You can also send me tips on coffee. This is never an obligation, but it's always appreciated. Also, in case you were wondering, yes, the character is based on Dirk Gently. I love those books and the BBC America show as well. I actually wrote a whole novel based on it. I doubt anyone cares, but I'll put it in the description anyway. Thank you again for watching, and see you in the next one. Bye.